we will be discussing more in depth about how quantum states can be used to split or share a classical secret. And the reason is a lot of the literature today has focused on this, and this is an easier protocol to implement. Teleportation has also been implemented so far in practice, as well as there are demonstrations of error correction, partly both of these put together. There are not too many works that have tried to perform quantum secret sharing with quantum states that are distributing a quantum state. So here we are going to talk about now how GHZ states can be leveraged to share a classical secret, and we will subsequently also discuss how one can generate GHZ states. So let's look at this high-level picture. There are again going to be three N-node users in a quantum network, Alice, Bob, and Charlie. They have a GHZ state that is distributed and shared across them. Each has a photon from the GHZ state. And how does the protocol go about in this case? They each measure their photon in X or Y basis, and they publicly announce the basis choice. And here we'll see so many analogies with the BBM92 protocol, where similarly the users of the network who want to share a secret key, just two of them, they perform basis measurements and pick between two basis choices, and the basis choices are publicly announced. However, the measurement result or outcome is something they keep as a private bit. The same happens here, and compatible rounds are decided based on the basis choices that each of the parties announces. And we will try to see an example here. We have a table here with rows representing the different basis choices and outcomes that Bob can measure. And the columns represent the same for Charlie, and the elements in the table marked in blue are the states that would represent Alice's outcome and basis if all the three would be correlated. So let's, for example, consider Bob measuring in Y basis and having a measurement outcome 0, Charlie measuring in Y basis and having a measurement outcome 1. If Alice measures in the X basis, then Charlie and Bob can be certain that her private bit or the measurement outcome is 0, and that would be the secret bit. Only if Bob and Charlie collaborate and share with each other their measurement outcomes. So if Alice measures in Y basis in this case, that particular round of sharing is marked as unsuccessful. However, if the basis choices result in correlated results, then they call that as a successful attempt. And very similar to what we discussed before, even in this case, it is essential that Bob and Charlie have to collaborate and put their shares together to reconstruct the secret bit, and they cannot individually reconstruct it. Individually, their photon is essentially in a mixed state. It's only when they consider the joint state that they can learn about Alice's secret bit. And we've discussed about eavesdropper detection as well, essentially backed by no cloning theorem. It's not possible for us, for an eavesdropper to go undetected over when Alice and Bob and Charlie are able to make several measurements and compare the error rate of their distribution protocol. They will be able to identify if the error rate crosses the threshold, that there is an eavesdropper's presence, and they should use a different link or mark this as a link that is vulnerable to eavesdropper. So with that, let's also delve into how one can scale this to multiple parties. And in this case, one would rely on a multipartite GHZ state. Specifically, let's consider an n-partite GHZ state. Similar to the protocol we just discussed, each of the end users in the network, they're going to have one photon from this multipartite state, and they each are going to perform basis measurements either by picking X or Y basis. To really understand how this works and how the selection or decision around which round is compatible and is going to have correlated results and which round isn't going to have correlated results. So, which round is successful, which is unsuccessful. In order to decide this, let's look at how the transformation occurs for each of these basis measurements. Specifically for this, we will see how Y basis can be represented. In this case, we can I understand it as or represent it as first applying a phase flip operation or Z gate, or not applying that, in which case it would be identity operation, followed by an X gate operation. Whenever the phase flip operation is applied, since the Y basis can be represented as a phase flip followed by a bit flip, which is X operation, one can identify that that would be the Y basis in which the measurement was performed. And in the second case, when an identity gate is applied, followed by a bit flip or X gate, that would just be X gate being applied. So having understood that, let's see the action of phase flip or identity operation on this GHZ state. So here we have an expression where all the different phases that are accumulated based on application of phase flip or identity operation is written down in terms of the terms alpha 1 through alpha n that are all combined in this term that goes into the GHZ state. They're all occurring in the exponential. These are phases, and they can either take a value of 0 if identity was applied, or pi if the phase flip or Z gate was applied. And another property that we will rely on is that GHZ correlation or GHZ state, when each of the photons in the GHZ state is applied a bit flip, it's going to retain the same state. And this is very easy to see. You have 0, 0, 0 terms and 1, 1, 1 terms in the GHZ state. If you flip the bits, the exact same state is recovered. So how do we combine these two and understand in which case do we recreate the correlations that we need? Specifically, if we look at this, we can understand that only when we have even number of phase flip operations that are applied, that is when we can be certain that the same state is recovered, because even number of phase flips means that the phase is a multiple of 2 pi, and you have recovered the GHZ state, and all the measurements are correlated in this case. However, if there are odd number of phase flip operations applied, then that particular round is termed as unsuccessful because you're not recreating the same exact state that you started out with. So with that in mind, let's come back to like summarizing this whole protocol. Even in this multipartite GHZ state scenario, there is a single dealer and there are n-1 players, and n-1 players in fact have to collaborate and bring their shares together. All of those n- shares are required in order to reconstruct the secret that the dealer has shared, and this just originates from the secret sharing protocol, relying on GHZ state in this particular case, that the threshold is n-1. The entangled state requires that in order to know what one of the photons collapsed during a measurement, all the rest of the measurements have to be combined.